So section 4.3 has really two big major topics in it. One is a Riemann sum, and that's when delta x doesn't necessarily have to be constant anymore. We play that trick so that when we evaluate our function within the limit method with sigma, we don't get these crazy things like square root of I. We get I, or I squared. But the other half of this particular section has to do with a very important topic called definite integrals. Now, I want to show you what a definite integral is. And a definite integral has to do with using the integration symbol, which is an antiderivative, but we're actually not going to execute the antiderivative. I just need you to know what it means when we use the terminology of a definite integral. The difference between this integral and the ones we've done previously, which you do have to do the calculus on and find those antiderivatives, ultimately we will on these two, but the big difference is we put what's called limits of integration, and they're not limits like LIM limits. They're starting and stopping points. Basically, just like we have been doing all along for areas. We start at A and we end at B. So let me show you the terminology for definite integrals. If you had a curve, f of x, and you started here at A, and you stopped here at B, and you wanted the exact area underneath this curve. Well, right now, the only method you have is to use the limit. So the area should be the limit as n approaches infinity of a sum of rectangles, where each rectangle has a height and each rectangle has a width. And we'll stick with a constant delta x. You next would calculate what delta x truly is, b minus a over n. And also, you would next compute the pointer for x, x1, x2, x3. The way to get to those x's, start at home, which is a, and add this many delta x's over to get to that specific x. And then, of course, this has to get injected into the function, and then you have to run the function. So this is one way of getting the area beneath a curve. The terminology we use in calculus to get the area beneath a curve involves the use of this integral symbol. And in fact, what you do is you integrate the function. Now remember something about the antiderivative symbol. Each antiderivative symbol must have a bookend, which is dx or ds or dt or whatever the independent variable is. Without this, it's really meaningless. You have to have this as a bookend. Don't forget to have it. Now wait a second. Area is the antiderivative. That doesn't make any sense. The antiderivative is a function. It's capital F of x. You know, it's like x cubed over 3 or something like that. That's not an area. That's a function of x. I need a number. I need a number. So how are we going to get a number here? Well, the terminology for a definite integral, in which we get a definite answer, a number, we need to put our limits of integration in here and put one here. This is my starting point, A. This is my stopping point, B. Now, here's the concept. The integral symbol looks like an S. And S stands for sweep. It's a clean sweep of area. So you're literally sweeping out area from A to B. That's what I think about when I see that integral symbol. In fact, what the integral symbol, this sweeping, is also is a sum. So that integral symbol must have some connection with the sigma right here. In fact, it has a very direct connection with sigma. Now, you know how sigma works, and you know what we did before. We used to add discrete rectangles that had a discrete delta x that you could see with your eyes, and a height, f of x sub I. So it was height times width. So what's this? This is not a discrete sum like this one is. I'm going to call this a continuous sum. And a continuous sum means we don't stop to build rectangles. We just continuously sweep out area. And we don't have any ragged edges whatsoever. It's almost like painting. You're just sort of painting the area in here, just like that. And that's what this thing does for me. It's a continuous sweep. All the while, what is it summing? Check this out. F of x, that's the height. What is dx? Well, you probably remember from differentials that dx and delta x are very much related. Dx is a little bit of x. In fact, dx represents delta x approaching 0. It is the old delta x, but approaching 0. So dx is not 0. It's as thin as humanly possible. It's delta x trying to get to 0 without ever reaching 0. So what is dx but the width? And what is my width on these rectangles? They are hair-thin rectangles painted right next to each other. I mean, the width is basically as thin as you possibly can imagine. So I read this definite integral as I want you to S for sum, sweep out, my height times my infinitesimally thin width, and get me the area beneath that curve. So you're still kind of summing rectangles, but the width of each rectangle is incredibly thin as possible, okay? And the f of x, of course, is the height of the rectangle. So you see how these two are connected right here? They are very much connected to each other. Now, without actually doing the calculus behind a definite integral, I think we can maybe look at a few examples to come up with the result of area. The first one I'm going to do is very simple. I'm going to just do f of x equals x. Now, if I want the area from, let's say, from 0 to 2. And we're not going to do this with the limit method anymore. We're going to say that the area equals a clean sweep or sum starting at 0, ending at 2 of these hair-thin rectangles, right? Here they all are, hair-thin piled up next to each other, where the height of each rectangle is just f of x, that's y, that is the height, and the width of each rectangle is dx. This is my infinitely thin width, incredibly thin width. dx always represents a little bit of x. It's not 0. It's delta x approaching 0 is what it really is. It's as thin as possible. So think of this as a sum or a sweeping out of area of these height times widths, where the widths are very, very, very thin. Now, I'm not going to use the limit method. I'm not going to use calculus because we have a geometric formula for this. We don't need anything fancy to find the area of a triangle. So from 0 to 2 is 2, but f of x is x, so the height is 2. So the area of a triangle is 1/2 base times height, or 1/2 base times height, or 2. So using this new terminology, we would say that if you integrate from 0 to 2 on the f of x, that's x, f of x just in this case is x, dx, the answer must be 2. And that's not really doing any calculus on the problem. We're just using the terminology. The definite integral is the area of the region beneath the curve up against the x-axis. Okay. So here we got 4 minus x squared. you remember, we sliced and diced here, and we ended up getting our area. But we did it using the limit method. N approaching infinity, we sum from I equals 1 to n, the f of x sub I times delta x. And what did we end up getting? 5 1/3 was the exact area. Now, I don't have a geometric formula for a parabola, an area of a parabola. But I can say this, that the area from 0 to 2, because we start and stop, on my function f of x dx, which would be the sweeping out area from 0 to 2 on this function, 4 minus x squared dx, has got to be 5 1/3. So honestly, we're not doing any calculus right now. I'm just using the terminology for the definite integral. And in fact, in this chapter, that's really all we do. That's as far as we get. Let's try another one. I wonder what this area would be. Let's go from -2 to 2. On the square root of 4 minus x squared. Now this says sweep out area beneath this curve, which is the little f of x, starting at -2 and stopping at 2. That's what it says, and that really is what this particular chapter is all about, is translating what this definite integral means. We want the area beneath the curve f of x, square root of 4 minus x squared, from x equals -2 to x equals +2. I think a picture here will really reveal what we need to do here. The function is y equals the square root of 4 minus x squared. If you square both sides, you get y squared equals 4 minus x squared. If you add x squared to the other side, you discover that in reality, this function is part of a circle. Now, it isn't the whole circle because it's just the positive y's on the circle. Let's draw it. Isn't it true that r equals 2? X squared plus y squared is r squared. So here's my circle, guys, and it's only the top half. Now, let's translate one more time. Area is the antiderivative. It's a definite integral from -2 sweeping to 2. So we sweep out area under this curve. dx just means that's a reminder as to what the independent variable is. And it is actually a very thin slice of x. So what's really going on, here's the movie, is that we're getting these tiny, tiny hair-thin slices of x. And they're all continuously sweeping or painting the area under the curve. This is really the movie of what's going on. And they're incredibly thin. And that's what dx is. dx is that incredibly thin dimension. Now, all these rectangles have heights, and what are their heights? Just f of x. That's where you get heights from. And there's your area. But wait, we can calculate that area. The area of a circle is pi r squared. The area of a semicircle, or half a circle, would be pi r squared over 2. R is 2. So the area of this semicircle is pi 2 squared over 2, which is 2 pi. So, I think we can now say with confidence that the area, which is represented by sweeping out area under a curve from -2 to 2, under this curve, and the interesting thing about it we didn't have to do any calculus, really. We will later do calculus. We will actually do the antiderivative. For right now, I'm just trying to formalize the terminology. The definite integral, what is it? It's the area under the curve. We will end up doing calculus on this, but right now, we're just establishing the terminology. Now, properties. The properties of definite integrals. Think about this one. What is the area beneath the curve, f of x? Every integral or antiderivative needs a bookend, a dx in this case. And what if I integrated from a to a? What would you get? That says start at a and sweep, well, wait a second, stop at a. So this continuous sweeping painting motion never actually took place. So all you've got really is that maybe that one rectangle. That's it. But the one rectangle has this infinitely thin width. In fact, delta x is going to 0. It's just so small that there really is no area in that one tiny hair-thin line. I don't think we picked up any area at all. So that is one of our special definite integrals. Something else to note. If you were to ask for the area from a to b on a function, and then you went ahead and reversed those limits of integration, you would think you'd get the same result. Whether you paint under the curve from a to b or you paint from b to a, what should be the difference? You will get the same numerical area. But when you do it the wrong way, when you do it in the opposite direction, the area actually changes sign. So that's one thing to note as we get towards the actual antiderivative when we actually execute this with calculus. We haven't quite done that yet. You will notice that integrating from a to b is different than integrating from b to a. There's a reversal in the integration process, in the painting process, and you actually do get an opposite sign. So yes, we do get negative areas sometimes. In fact, here's something to note as we get further into this. If we just stick with going from left to right, a to b, and we have area that is above the x-axis, you'll get a positive answer. If we again stick with going from left to right, a to b, we don't reverse it like we just did. But what if the curve lives below the x-axis? Turns out that that area will come out as a negative area. Now, I know there's no such thing as negative area. There's no negative area of a circle or a square. But when we compute area, we will get negative area because think about how it's really being calculated. We're using height times width. Now, the widths don't change. They're all those little hair-thin dx's, so those are all, you can consider them to be positive. But when the curve lives below the x-axis, the heights are all negative-wise. And so you're summing up multiplication of height times width, a negative height times dx, another negative height times dx, and they all add up to be a negative quantity. So area that lives below the x-axis is considered to be negative. Area that lives above the x-axis is considered to be positive. Let's look at another property, and this is called the additive interval property. The additive interval property looks like this. If I were to have a function like this, and I asked you to do two things. I said the first thing I'd like you to do is can you sweep out or compute the exact area under here, and then also sweep out and compute the exact area here. We have terminology for this now. I know we could use the limit method, but we have the symbols of using the antiderivative or integration symbol. The first one would be, and this is f of x, area 1 would be the definite integral. We normally do this from left to right, so from a to c of my function, and we always have that bookend dx. What if I were to add that to the next one, area 2? The second one would be integrate, pick it up from c, sweep across to b, again of underneath my function. And think about it for a second. Wouldn't that be also equal to this? What if you just swept directly from A to B? You'll get the same area. So we call that the additive interval property. And it means basically you can get the area under a curve in different segments. Really all we did there is we paused at x equals c. So we were sweeping out area, and then we kind of paused at c, and then we picked it up from c and went on to b. But whether you pause at c or you don't pause at c, you're going to get the same area nonetheless. So we call that the additive interval property. Now, a couple other features of definite integrals. And again, we're not really doing the calculus aspect of that. That comes up next. And if you were to integrate from a to b, meaning area underneath a curve, of a constant multiplied by a function like this, we do know from our antiderivatives that the constant can come out front. And then we would get the area under this curve. And if this curve formed some geometric feature, then we could get the area using a geometric formula. But if it's not a geometric feature, then we probably will have trouble getting the area, and maybe we'd have to resort to the limit method. Another property would be the additive property here, addition and subtraction. If you have two functions added or subtracted, and you want the area under that addition or subtraction, we can actually do this separately. And we've done this separately before when we did our antiderivatives or our indefinite integrals. And it's certainly a whole lot easier to deal with one function at a time and say, what's the area from a to b on that one, plus or minus what's the area from a to b on that one. We certainly have that ability. Okay. Now they give us an example of this, and they say, could you tell me the area from 1 to 3 underneath this quadratic minus x squared plus 4x minus 3. Now, of course, the antiderivative symbol is really no good without a dx. First thing you can do is break it up. We'll do this. You can bring the constant multipliers out front. And then finally, bring the constant multipliers out front. I'll put a little 1 in there just as a friendly reminder that there really is a 1 there. Now this one, this is the area underneath this parabola right here from 1 to 3. That is not a geometric object. So the only way you can really get that area is to use the limit method. I'm going to avoid that by just giving you that answer. So had we done the limit method, you would have realized that the area is 26/3. So just kind of shortcutting that particular area. But yes, you would use the limit method on this. Delta x be minus a over n. X sub I is a plus I delta x. And then you'd have to go through that whole process. So right now, the area beneath the big parabola, this guy here, starts with a minus 26 thirds. Plus 4 times this area. What is the area beneath the x curve? From 1 to 3. Now that is a geometric object. You can get that area by either calculating the area of a trapezoid, or you could actually get the area of two triangles. I think that's probably an even better idea, because since we might not have the trapezoidal formula available to me. So what I'm going to do is get the area of the big triangle. Area of the big triangle is 1/2 base times height. This is y equals x, so the height's the same, minus the area of the little triangle, which would be 1/2 base times height. And that's to subtract off this area of that little guy. That gives me the area from 1 to 3. What do we got here? 9/2 minus 1/2 is 8/2, or 4. So this integral here is worth 4. The area underneath the x curve, and I did it geometrically, minus 3. And this thing here says, give me the area beneath the curve, y equals 1, from 1 to 3. So let's do that. Well, as luck would have it, another geometric formula can be used, because that is just the area of one big rectangle. And it's a 2 by 1, and 2 by 1 makes 2. So as you can see, I actually went through this problem. I didn't use any calculus at all. I skipped the limit method only because I did it previously and got the answer for you. 26 thirds would be that area there. But these two I was able to get simply with geometry. So in the end, what's our overall limit going to be? It's going to be minus 26 thirds plus the 16 minus 6. And if you tally that all up together, you get 4 thirds. Now, as a reality check, what you could do is you could graph that original parabola. You could look between 1 and 3 and maybe do an estimate to see if the area really should be roughly about 1. So good thing to do. Now, you got to be careful, because what happens on problems where some of the area rests above the x-axis and some of the area rests below the x-axis? It turns out that those areas will cancel themselves out, because you have some positive area that registers, you have some negative area, and you got to add them together. So one last problem to take a look at, and again, we haven't done any calculus. We haven't even needed the limit method on this definite integral work. Let's finish with this, guys. I would like the area underneath this curve from 0 to 2 pi on my sine curve. Now, if I graph sine from 0 to 2 pi, I think you're familiar with what a sine curve should look like. It goes from here up to 1, goes down here, back to 0. Now it goes down to minus 1 over here, and then back to 0. So my curve is symmetrical, and it looks like this. We'll sketch it in here. Goes down here, turns around the corner at minus 1, and then back up here. Now wait a second. I'm asking for 0 to 2 pi. So this is going to be some positive area that lives above the x-axis. This is going to be some negative area that lives below the x-axis. And you have to add this area to this area. But it's symmetrical. The area up here should be a match to the area down here. But this is positive area, this is negative area. the answer should be 0. So that's the other thing to take note of, and that is when we deal with area, we do have negative areas when we're talking about the area beneath a curve. And that is from the curve up to the x-axis, and if the curve lives below the x-axis, that area computes out to be negative. And we're adding all the areas together, so what's weird about this problem is we know the answer is 0, and yet we don't really know the answer to this problem. We'll certainly find out at some point, but I can give you the rough guess. Here's a really rough guess. If I were to draw a rectangle from 0 to pi, my rectangle would be pi times 1. So I can't say equals. I'm going to say roughly equal. So my big rectangle is pi. But how much of this curve is consuming that rectangle? I'm just going to guess. I'm going to say roughly 2/3 of that curve. So my roughest guess here is 2 pi over 3. Is it correct? I'm not sure. We need to do some more work to find the exact area beneath that curve. And I'm not going to use the limit method anymore. I'm going to start using calculus, because I've been drawing the antiderivative symbol, I've been drawing the integral, and I've never really executed it. I've just used it for the new terminology that we're learning. The next thing we're going to do is we're going to execute the antiderivative. In other words, for this problem, the antiderivative of sine is going to be minus cosine. And then I'm going to have to do something with the 0 and the pi. We'll get there. But for now, I did want to make sure that you knew that the terminology for talking about area from a curve to the x-axis is to use that antiderivative symbol, use the integration symbol. We call it a definite integral when we put the limits of integration in there. Thanks very much. And the next series of videos, we will be getting the area under the curve by doing calculus, not using a geometry formula. Thanks very much.